Yesterday, we started talking about equilibrium. So by definition, equilibrium is established when what has happened? Yeah, the two rates are equal. So the forward and the reverse rate are equal. We're said to be at equilibrium. So for the forward rate and the reverse rate to be equal, the reverse rate has to exist, right? So if a reaction is not reversible, can it have a reverse rate? No, it's just zero, okay? So for a system to be at equilibrium, the reaction has to be reversible. So it has to have the double arrow. Most of the reactions we've looked at this year are not reversible. Let's look at a few of those and think about why for just a second. So if I have this generic reaction, A solid plus B, C, AQ, what type of reaction does that kind of look like? Single replacement. So it says a plus 2 metal, it's a plus 2 metal, that's a minus 2 metal, or minus 2 non-metal. So rather than just go ahead and writing the products, what are you going to check first since it's single replacement? What? So what do you check though? The activity series. So I look at the activity series, and the question I'm asking, is A reactive enough to replace B? Right? So let's say I go there and I say the answer is yes. Then I get A, C plus B. So I have found that A is reactive enough to replace B. So for the reverse reaction, that would also be what type of reaction? Single replacement. Okay? Now B is trying to replace A. Do I even need to consult the activity series to find out if that can happen or not? No. If A is more reactive than B, can B be more reactive than A? No. So both ways can't happen. You can't have both metals reactive enough to replace the other metal. So that's why we won't see a reversible single replacement reaction. So eventually, will I run out of either A or BC and the reaction just stop? Yeah. So we've always done. Limiting reactant stops it. With equilibrium reactions, we said they never stop. The rates just equal and they're constantly going back and forth. But with non-reversible reactions, they just stop. You run out of something and we're done. So single replacement reactions are not reversible, so we cannot have equilibrium. If we look at an example of this type of reaction, where I have AB AQ plus CD AQ yields AD solid plus CB AQ, what type of reaction is that? Double replacement. Did that double replacement reaction happen? I heard a yes. How do I know it happened? Do I have to check anything? Based on what I gave you, do you have to check anything to see if it happened or not? No, I told you it's already a solid product. So if I have a solid product, the reaction happens. So I found that by using the solubility table. I found that AD is insoluble, therefore the reaction happened. But let's look at if I wanted to go the opposite direction, the reverse reaction. What would AD have to do for the reversible reaction to happen? Have to dissolve. Is it soluble in water? No. So can the reverse reaction happen? No. So is this a reversible reaction? No. So is it okay to write the arrow like that? No. It is not reversible. So will it have or experience equilibrium? No. Something's going to run out. When we run out, we're going to be done. That's going to be the end of it. So most of the reactions we've looked at this year are non-reversible. Those are the more simple ones to begin with. However, in the grand scheme of chemistry, most reactions are reversible. And we're going to start looking at more and more of those. Most of the reversible reactions, I said that backwards. Most reactions are reversible in chemistry. I said that backwards, sorry. Most reversible reactions involve covalent reactants. And we'll begin to look at more of those. So we started off briefly talking about Le Chatelier's principle in relation to equilibrium processes. So what does Le Chatelier's principle tell me? Or what is it in your own words? Anybody? Without just reading it. Does the word at least sound familiar to you?
Yes.
There we go, we're somewhere. So essentially, we said that if you make some change to an equilibrium reaction, the reaction is going to do something to alleviate or counteract that change. Okay? So this is worded, if you stress a reaction, it's going to do something to undo that stress. Okay? If I give you a test tomorrow, you're going to be stressed. So you're either going to study tonight to alleviate the stress or just accept defeat. But either way, you're going to alleviate the stress you have. Okay? The reactions are the same way. No matter, or typically, whatever stress you apply, they will do something to compensate for that. And they will do something to partially undo the stress you induced. So the examples of stressors that we gave, the first was adding or removing something. So if you add a product or reactant, or you take away a product or reactant, that is stressing the reaction. It's putting a change to it. Another common change is increasing or decreasing temperature. So when you increase or decrease temperature, the reaction does something to compensate for that, to try and even that out. And the third was increasing or decreasing, changing pressure. You might want to make a note that really only applies to gases. We aren't super concerned if we don't have a gas. If I have 3 liters of gas, can I pressurize that gas and force it into a 2-liter container? Can you put 3 liters of gas in a 2-liter container? Yeah, you can increase the pressure by decreasing volume. But if I have 1 liter of solution, can I force that into a 0.5 liter container? No, we can't pressurize solutions to make them fit into smaller spaces. So we typically just care about the gases in relation to pressure. So in a couple of days we'll look at quantitatively how to decide which way equilibrium shifts. But now we're just going to answer, does equilibrium shift left or does it shift right? What I mean by that is, if it shifts to the right, we're using more of the reactants to make more product. Okay, the rate of the forward reaction increases, so we get more products. If I say it shifts left, that means the reverse reaction is happening more quickly. So we're using more products to make more reactants. So when I say shifts left or right, just think about, am I going to make more products or make more reactants? The most common mistake relates to temperature. People just try and memorize when you increase or decrease temperature, what happens. And we can't do that. In order to know which way a temperature change shifts equilibrium, what do I have to know about a reaction? Whether it's, what? Yeah, endothermic or exothermic. If it's exothermic, energy is a product. If it's endothermic, energy is a reactant. So in one versus the other, increasing temperature either adds more of a reactant or adds more of a product. Okay, so you can't just memorize that. So we did, I think 1 through 4 yesterday, right? Examples. So let's look at it's labeled generic example there. So I have a reaction, and for rates, it was not super important that I balance the reaction, but for equilibrium it is. So the reaction's balanced. What can you tell me about that reaction? It is, what word describes it? It's reversible, even though the arrow is hard to see. What else? What? It's exothermic. What type of reaction is it? It's synthesis. Okay. So we have a reversible exothermic synthesis reaction. That'd be a good exam question in May. So now let's look at the questions. Question 1 says increasing the temperature will cause the reaction to shift to the blank. So temperature is associated with energy. So if you increase temperature, are you adding energy or taking away energy? You're adding. So I'm going to add energy. So if I increase the amount of energy, the reaction will say doesn't like it, for lack of a better way of saying it. So if it doesn't like it, what can it do to kind of compensate for that? It can. So what does shifting to the left do, though? It uses up some of the energy, right? The left reaction is AB2 plus energy makes this. So if I do more of the left reaction, am I using up some of the energy that I put in? Yeah. So does that partially fix the problem that I created? Yeah. So we can say it will shift to the left. If you want to write an explanation, you can say to partially use up the energy that was introduced. So now let's think about the amounts of reactants that I have. Is increasing the temperature going to cause there to be more of A or less of A? More. So shifting to the left means we're doing more of the reaction going that way, towards the reactant side. So if we do more of that reaction going to the left, am I going to have more of A or less of A? More. So I can say the concentration of A increases. But then, what about the concentration of AB2? Am I producing more AB2, or am I using up more AB2? Using up more of it. So will the amount of AB2 that I have go up or go down? Go down. So that's what I mean by shifting to the left. We're going to make more A and B and have less of AB2. Okay, the reaction in that direction is favored. We're producing more of that. Okay. So then B, or 2, whatever you want to call it. Increasing the concentration of A shifts to the blank. So I have A, I increase it. How can that reaction compensate for me adding more A? Shift to the right. What does shifting to the right do to A? Yeah, it uses it up, right? So if I shift to the right, I use up A. So if I use up A, does that partially compensate for the change that I made? Yeah. I'm going to shift to the right. So what is that going to do to the amount of B that I have? So let's think about it. Am I going to make more product or less product? More. Do I need more B to make more product? Yes. So if I use more B, does the concentration of B increase or decrease? It decreases because I'm using it. So I'm using more of B to make AB. So the concentration of B decreases. But the concentration of AB is going to do what? Going to increase. So if I'd given you this just 3 months ago, you probably would have gotten it right. If you add more A, more reactant, probably going to make more product, right? This should be kind of logical. Add more reactants, you get more products. So then C has to be the opposite of B there, the third one. So if we did the second one right, the third one's got to be left. Opposite changes have opposite effects. But let's look at it to make sure we're right. So now I'm going to decrease B. A, sorry. So if I take away A, what does the reaction want to do to make up for that? It wants to make more A. Okay? How does it make more A? Shift to the left or shift to the right? Left. Is that the opposite of my previous answer? Yeah, so we either got them both right or both wrong. So now, what can I say about these two answers? They're going to be the opposite, right? So if it shifts to the left, I'm making more B by using up AB2, so I have less of that. Okay, so I can say concentration of B increases, concentration of AB2 decreases. Does that make sense? Good. Now the last one, do I have enough information to even answer that last question? Now, what do I need to know about the reactants and products to answer a question about pressure? I need to know what they are, right? If they aren't gases, does pressure matter? No. So let's assume they're all gases, okay? You never have to do that. It'll be typed out. That should have said gases, but these are all gases, okay? So how many gas reactants do I have? 1 plus 2 is how many? 3. So 3 gases becomes how many gases? 1. So to increase pressure, what do I do to volume? Decrease it. So an easy way to think about it, and remember it is, what fits better in a smaller volume? 3 gases or 1 gas? 1 gas. So which way does it shift? To the right. So an increase in pressure favors the side with the fewer gases. A decrease in pressure would favor the side with more gases. So it's the opposite there. Okay? Let's look at a different example though. Let's just say I have A aqueous plus 2B aqueous yields C gas. So if I have that example and I increase pressure, which way does equilibrium shift? To the left or the right if I increase pressure? To the left. How many total particles are on the left? 3. How many of those are gases? 0. How many gases are on the right? 1. So which side has fewer gases? The left. Does it have fewer particles? No, it's fewer gases though. And pressure is concerned with the number of gas particles. Okay? Questions about that? Okay, so we don't want to try and memorize when this happens, that happens. We want to look at each example case by case and try and decide what it's trying to do. What can the reaction do to compensate for the change that I made? So if you look below, there are 12 questions.